two minor loss problems for the price of one. Both of these problems have fluid flowing from one tank to another, but they go there in different ways. In the first problem, we've got elbows and a valve, and on the other problem, they're going through a sudden expansion. They're going to both start off using the energy equation, which is just the Bernoulli equation with head loss. But for head loss, we're using both major losses due to friction, which is going to use the Moody diagram, and also a new concept, minor losses, which has to do with all of these extra things like the elbows and the expansion. But the good news and the best news for you is that the actual minor losses part of this is definitely going to be the easiest part of the problem. So by the end of this video, you're going to feel like a genius because you'll see that, that actually is kind of easy. So for this first problem, right, we're going to be trying to find flow rate in meters cubed per second from tank A to tank B. Right, this is going to be an energy equation problem using the Moody diagram of minor losses, and I'm going to leave the assumptions blank at the start because I don't know what assumptions I'm going to need to make, but every time I make an assumption as I go through the problem, I'll write that back here at the start. We might as well start off working backwards, so if the final answer is going to be Q, volumetric flow rate is area times velocity, so pi over 4 d squared is the area, 0.007854 meters squared. We don't know velocity yet, so actually that's kind of the main part of the problem here. Once we solve for velocity, we'll come back and plug that in here and solve for volumetric flow rate. So this problem falls under the category of conduit flow, right? Flow through pipes. This is always going to involve the energy equation. So you're going to pick two different points and connect them to each other, so points along a flow line. So I'm going to choose point A and point B at the top of each tank, because a lot of terms cancel out on the top of each tank. So if you have a tank in your problem, that's almost always the best choice for where to choose. So energy equation, PA divided by gamma plus V squared A over 2G plus ZA, that's the height to point A, is equal to pressure at B divided by gamma plus VB squared over 2G plus ZB plus head loss. And now you can see where we cancel out a bunch of terms. Pressure on both sides is atmospheric, so those cancel out. And the velocity on both sides is also going to cancel out to zero because an assumption that we make is that the surface of the tank is changing slowly. This should not be confused with the velocity of the water through the pipe. Here I'm looking at the velocity of the surface level rising or falling. And if the pipe is small and the tank is really big, then the tank itself is not going to change volume very quickly. And this just leaves us with ZA minus ZB equals head loss. And we have this change of height on the drawing 2 meters. So we know that the head loss is equal to 2. So let's just find head loss. So the head loss is going to be a combination of both major losses and minor losses. So since this is a minor losses video, let's do the minor losses first. So for minor losses, we're basically just going to trace a path from point A to point B, and every time we get to like a new feature, there's going to be minor losses associated with that feature. So the first one we'll get to is this entrance. This is called a re-entrance, where the entrance isn't right at the edge. It's actually kind of stuck in a little bit. And so a re-entrance, I can look this up in the FE reference manual. They've got a table here of 0.8. for that value K. As I go through, the next feature I get to is a 90-degree elbow for a threaded rod, a threaded elbow. And I'm using the textbook by Elger, which has table 2.5, has some values here for minor losses. 0.9 for a 90-degree elbow. Now this valve, I don't know anything about it. The picture doesn't say what kind of valve it is. Is it open? Is it partially open? So now here's where I have to just make an assumption. So I'm going to make an assumption that this is a gate valve that is fully open. So I'll call this value 0.2 based on the table I'm using. But you could get something very different if you were using, different tables, different type of valve. So just make an assumption. Another 90-degree elbow, same 0.9, and then an exit. And for this exit, I can kind of stay here in my Elger table 10.5 and set D1 divided by D2 for an expansion equal to 0. Basically, it's going from a pipe into a gigantic space. And this is going to give me a K exit value of 1. So add all these up together, we get 3.8 as the value of K that's going to be used in the minor losses side. Bad news when calculating major losses is that we don't know velocity or F, and this is going to lead into kind of a loop where we need velocity to find the Reynolds number, we need the Reynolds number to find the friction factor, and then we have this head loss equation use the friction factor to find velocity, because velocity is the final answer that we want. So this is actually going to be an iterative solution. We just have to make a guess at a number, go through the loop and get back to our original guess. And if it matches, then awesome. That means we guessed right. But you're never going to guess right. There's like no chance. So just pick a number, any number. It really doesn't matter. You'll probably get to an answer within 1 or 2 or 3 guesses. So this isn't going to take forever, even if you have a really bad guess from the beginning. So I'm guessing 10 meters per second for my velocity. Reynolds number, velocity times diameter over viscosity. And I can never remember which viscosity is which, kinematic versus dynamic. So I always just check the units. I know velocity times diameter in the numerator is meters squared per second. So I take whichever viscosity value is in meters squared per second. So this is 1.31 times 10 to the minus 6 in the table that I'm looking at. Gives me Reynolds number 7.63 times 10 to the 5th. For the roughness value that I'm going to need for the Moody diagram, that's Ks over D. This will be another assumption that I have to make. So since this says it is steel pipe, I can look this up in my textbook and get a value of 0.046. If you look this up in the FE reference manual, you'll just see kind of a range of values, and 0.046 is in that range. So again, this might be one of those values for K that you make an assumption for, but so I'm going with 0.046. So I line these up, Reynolds number on the bottom, and the roughness 0.00046. There should be 3 zeros in there, and kind of line up those lines and see where they meet. I get an F value of 0.0176. And it's sort of hard to read, so if you are reading a slightly different number than this, that's okay, but you should be able to get like to 3 decimal places on the Moody diagram. It's not gonna be super accurate, but you should probably try to say 3 decimal places, because 2 is, you can see between the lines a little bit. So I plug this F value into my head loss equation, right? 2 is equal to FL over D plus K times V squared over 2G, where I've taken V squared over 2G and kind of pulled it out to the side. So I've got L is 14 meters, which is the length of those 3 sections of pipe, 4 plus 3 plus 7 meter length. 0.1 for the diameter, 3.8 was my value K. 19.62 is double gravity. And put in my friction value, get a V of 2.503 meters per second. Now, this is not 10, unfortunately. If it were 10, we would be done, and that would have been a miracle. But now we go through again. So again, it didn't matter which value you picked at the beginning. You're going to get a different value here, and just keep going. So guess again. Now, velocity 2.503. Get a new Reynolds value, 1.91 times 10 to the 5th. Same roughness coefficient, so I'm back to the Moody diagram, get a new F value, 0.0192, which now I plug back into the green equation again, and this time I get a value of V, 2.459. And at this point, the value V is only changing about 1%, so I think that's good enough. So I'm gonna go ahead and stop here and say that 2.46 is a pretty good velocity. Plug that back in what value Q, area times velocity is flow rate, and get 0.0193 meters cubed per second as the flow rate through this system. So one more problem to go. Still going from one tank to another tank on this new picture, but this time we're gonna use a sudden expansion in between instead of the valves and 90-degree bends. And this time, no iterative solution, so it'll go by a little bit faster. So we're given all the dimensions we're gonna need. We're also given Q, which is the flow rate, which is really good because we're gonna be able to use that to find velocity right off the bat. So that's gonna save us some time. And we're also given a roughness coefficient there, 0.1 millimeters. The thing we're trying to find is delta H, the height difference between the tanks. So how far lower tank B is than tank A. So this is going to be an energy equation, Moody diagram, minor losses type problem. So again, every conduit flow problem is just going to start off with the energy equation. So we start off identifying points A and B, like 2 points connected by a streamline to go in between. I'm going to start at the top of each tank, right? Because almost every term is going to cancel out this way. So pressure A over gamma plus VA squared over 2G plus ZA is equal to pressure B over gamma plus VB squared over 2G plus ZB plus head loss. Pressure terms cancel out as atmospheric. Velocity terms cancel because we assume it's 0 as the speed that the top of the tank is changing. And that just leaves our delta Z on one side, like the change in height, is equal to head loss. And the head loss for this problem is going to be really like 3 main sources. There's head loss 1 is going to be friction through the skinnier section of pipe. Head loss 2 will be friction through the fatter section of pipe. And then HLM, head loss minor, like all the minor losses in this problem. So we start off talking minor losses first. And again, just following the path from the entrance to the exit, let's just hit every time we hit a new feature, that's another minor loss. So the first one we get to is the entrance to pipe 1. Then we'll go through an expansion in the middle. So KV squared over 2G in the middle. And then also at the exit when it goes from pipe 2 into the big tank. That'll be another source of minor losses. So I can look up in the FE reference manual, a sharp entrance, right, without any rounded corners is going to have a K value of 1.0. And this will use the V in pipe 1, so I'm actually going to need velocities first. Fortunately, no iterative solution required. Q equals A times V, and we are given Q, and we can calculate A from the diameters. So we get V1, 8.842 meters per second, and V2 is going to be 2.215 meters per second, and V2 is going to be 1/4 of V1. So since V2 is, the pipe is double as big, right, that diameter gets squared, so it's 4 times the area, so the water will flow 1/4 the speed in order to get the same volumetric flow rate. So minor losses, again, if you look up in the FE reference manual, a sharp entrance is going to have a K value of 1.0. So then the 8.8 squared over 19.62, which is 2G. Then for the expansion, so in my textbook, right, the Algebra table 10.5 has a sudden expansion. In this case, D1 divided by D2 will be 0.5, and theta is 180 degrees, as in it's a sudden expansion. It just opens up to like 180 degrees, right? The 20 degrees would be like a gentle expansion. So with 0.5 and 180 degrees, I can sort of interpolate halfway in between the two values in the table and get 0.555 as my value for K. And for this expansion, I'm using 8.8 as the speed, not 2.2. So when going through an expansion or a contraction, either one of those, you use the faster speed. So the smaller section of pipe, which has the higher speed, use the higher speed when calculating head loss. So it doesn't matter if it's an inlet or an outlet, use the faster speed for contractions or expansions. For the exit, again, I'll go back to the FE reference manual. This is a sharp exit, so 1.0 for K, but this one is the slower speed since it's the fatter section of pipe at the exit, 2.2 squared over 19.62. Now, besides looking up sudden expansions in a table like this one, there's also an equation that you can use to find, instead of this 0.555 value for K, so instead of KV squared over 2G, you can actually use this equation that head loss through a sudden expansion is V1 minus V2 quantity squared divided by 2G. So you're not squaring each individual velocity, you're squaring them after subtracting. And notice that after you kind of work out this algebra, 8.84 minus 2.2, square it, divided by 19.62, you get 2.238 as the head loss through the expansion, which compare that to the value that I got using K was 2.212. And since that 0.555 was sort of interpolated, this is basically just within a rounding error. So looking up in the table or using this equation, either way, you'll get to the same correct answer. All right, so that's the minor losses, but we do still have to do the Moody diagram. We're not done quite yet. There is still friction, the major losses. So roughness value divided by D So for pipe 1, 0.1 millimeters divided by 120 millimeters. And again, it's always very good to write down your units because it'd be real easy to just write down 12 centimeters for the diameter or even 0.12 meters for the diameter. So make sure that your K and D, the units have to cancel out. So put them both in millimeters, 0.00083. For pipe 2, still 0.1 millimeter roughness divided by 240 millimeter diameter, 0.0003042. We'll need the Reynolds number before we can go to the Moody diagram. So velocity times diameter divided by viscosity. Again, I always forget which viscosity, so meters per second times meter in the numerator means the denominator has to also be meters squared per second. So this is 1 times 10 to the minus 6, and I'll go ahead and write that back in my assumptions just so that's kind of easy to find. Get a Reynolds number for pipe 1, 1.06 times 10 to the 6, and a Reynolds number for pipe 2, 5.3 times 10 to the 5th. Go to the Moody diagram using my roughness coefficients and the Reynolds number, 0.00083 and 1.06 times 10 to the 6, I get friction factor 1 of 0.0194. And then using roughness 0.00042 and Reynolds number 5.3 times 10 to the 5th, friction value of 0.0175. Can now plug these friction values back into the major losses equation, FL over D, V squared over 2G, 0.094 times 60 divided by 0.12, 8.8 squared divided by 19.62, head loss for pipe 1 of 37.86. For pipe 2, head loss of 2.188. So the head loss through pipe 1 is way more than the head loss through pipe 2, and this is because of velocity. The faster velocity, right, velocity ends up getting squared in head loss, so velocity is 4 times larger, and that value gets squared, makes the head loss 16 times larger through pipe 1 as compared to pipe 2. Since L over D, they actually both had the same ratio. Even though the diameter doubled for pipe 2, it was also twice as long. So now we combine all 5 sources of head loss, friction through pipe 1, friction through pipe 2, the entrance, the expansion, the exit, add together 44.5 meters of head loss. So that's how much lower tank 2 will sit as compared to tank 1, 44.5 meters. So if you're comfortable with minor losses, just looking up numbers in a table, but you want a little bit of extra review using the Moody diagram, right? That's probably the more complicated part. Then check out the video up on the screen here for more major losses example problems.